The webinar will cover the latest advances in alternating current motor and drive technology and how these advancements can improve the efficiency and productivity of operations. The benefits of high-performance alternating current motors and drives will be discussed. The process of selecting the right motor and drive for specific applications will be detailed. Guidance on the proper installation and maintenance of the motor and drive system will be given, as well as methods for troubleshooting common problems. Plant engineers, maintenance managers, design engineers, purchasing managers, and anyone interested in learning more about alternating current motor and drive technology should attend. The webinar platform used is Adobe Connect. A computer with an internet connection and speakers is required to participate. Testing the computer before the webinar is recommended to ensure the necessary software and hardware are present. During the webinar, the selection of appropriate alternating current motors and drives for different applications will be examined. Firstly, consider the load requirements including the torque and speed needed to perform the task. Secondly, look at the duty cycle, which is how often and for how long the motor will be running. Thirdly, determine the environmental conditions, such as temperature, humidity, and the presence of any hazardous materials. Fourthly, check the available power supply, making sure it meets the voltage, current, and frequency requirements of the motor and drive. After choosing the proper motor and drive based on the needs of the application, there are several aspects to consider during installation. Firstly, make sure the motor and drive are properly aligned to avoid excessive wear and vibration. Secondly, ensure the wiring is done correctly, following all applicable electrical codes and standards. Thirdly, provide adequate ventilation to prevent overheating. Fourthly, configure the drive parameters to match the motor characteristics in the application requirement. Lastly, test the system thoroughly before putting it into operation. To maintain the alternating current motor and drive system, several things should be considered. Firstly, regularly inspect the motor and drive for any signs of damage or wear. Secondly, keep the motor and drive clean and free of dirt and debris. Thirdly, lubricate the motor bearings as recommended by the manufacturer. Fourthly, monitor the motor and drive operating parameters such as voltage, current, and temperature, and address any abnormalities promptly. To deal with common problems, firstly, if the motor does not start, check the power supply, wiring, and motor overload protection. Secondly, if the motor is running but overheating, check the ventilation, load, and motor windings for insulation breakdown. Thirdly, if the motor is vibrating excessively, check the alignment, balance, and motor bearings. Fourthly, if the drive is displaying error codes, consult the manufacturer's manual for troubleshooting steps. Alternating current motors, ubiquitous in modern industry, convert electrical energy into mechanical energy through the interaction of magnetic fields. The fundamental principle behind their operation is electromagnetic induction, where a changing magnetic field induces a current in a conductor. These motors consist of two primary components, the stator and the rotor. The stator is the stationary part of the motor and houses the field windings which, when energized, create a rotating magnetic field. The rotor is the rotating part of the motor and it interacts with the stator's magnetic field to produce torque. There are primarily two types of alternating current motors: induction motors and synchronous motors. Induction motors, also known as asynchronous motors, are the most common type, operating on the principle of electromagnetic induction. The stator's rotating magnetic field induces a current in the rotor windings, which then creates its own magnetic field. The interaction between these two magnetic fields produces the torque that drives the motor. Synchronous motors, on the other hand, have a rotor that rotates at the same speed as the stator's rotating magnetic field. This is achieved by either using permanent magnets in the rotor or by supplying direct current excitation to the rotor windings. Synchronous motors are often used in applications where precise speed control is required. Alternating current drives, also known as variable frequency drives, or VFDs, are electronic devices that control the speed, torque, and direction of alternating current motors. They do this by varying the frequency and voltage of the power supplied to the motor. A typical alternating current drive consists of three main sections: the rectifier, the direct current bus, and the inverter. The rectifier converts the incoming alternating current power to direct current power. The direct current bus filters and stores the direct current power. The inverter converts the direct current power back to alternating current power, but at a variable frequency and voltage. By controlling the frequency of the power supplied to the motor, the drive can precisely control the motor's speed. Lowering the frequency decreases the motor speed, while increasing the frequency increases the motor speed. Additionally, the drive can also control the voltage supplied to the motor, which affects the motor's torque. Reducing the voltage reduces the torque, while increasing the voltage increases the torque. Alternating current drives offer several benefits over traditional motor control methods. Firstly, they can significantly improve energy efficiency by reducing motor speed to match the actual load requirements, avoiding wasted energy. Secondly, they provide precise speed and torque control, which is essential for many industrial applications. Thirdly, they can reduce mechanical stress on the motor and driven equipment by providing smooth starts and stops, extending the lifespan of the equipment. Fourthly, they offer advanced protection features, such as overload protection, overvoltage protection, and undervoltage protection, safeguarding the motor and drive from damage. There are several factors to consider when selecting an alternating current motor for a specific application. Firstly, the power requirements of the application must be carefully evaluated. The motor must be able to provide sufficient torque to drive the load at the required speed. The power rating of the motor should be selected based on the continuous load requirements, with some margin for occasional peak loads. Secondly, the speed requirements of the application must be considered. The motor's rated speed should match the desired operating speed of the driven equipment. If variable speed control is required, an alternating current drive should be used in conjunction with the motor. Thirdly, the environmental conditions of the application must be taken into account. The motor should be selected with an enclosure rating that is appropriate for the environment, such as totally enclosed fan-cooled or TEFC for dusty or wet environments, or explosion-proof for hazardous environments. Fourthly, the voltage and frequency of the power supply must be compatible with the motor's ratings. The motor's voltage and frequency ratings should match the available power supply to ensure proper operation. Fifthly, the motor's efficiency should be considered, especially for applications where the motor will be running continuously for extended periods. High-efficiency motors can significantly reduce energy consumption and operating costs. Similarly, selecting an alternating current drive requires careful consideration of several factors. Firstly, the motor's voltage, current, and power ratings must be compatible with the drive's ratings. The drive should be sized to handle the motor's full load current and voltage. Secondly, the application's speed and torque control requirements must be considered. The drive should be selected with the appropriate control features, such as variable torque, or constant power control. Thirdly, the communication requirements of the application must be considered. The drive should be selected with the appropriate communication protocols, such as Ethernet, Modbus, or Profibus, to allow for integration with other control systems. Fourthly, the environmental conditions of the application must be taken into account. The drive should be selected with an enclosure rating that is appropriate for the environment. Fifthly, the drive's harmonic distortion should be considered, as high harmonic distortion can negatively impact the power quality of the electrical system. Drives with built-in harmonic filters or reactors can be used to mitigate harmonic distortion. The installation of alternating current motors and drives should be performed by qualified personnel following all applicable electrical codes and standards. Firstly, the motor and drive should be properly grounded to ensure safety and prevent electrical shock hazards. Secondly, the wiring should be sized correctly to handle the motor's full load current, and the connections should be tight and secure. Thirdly, the motor and drive should be mounted securely to a stable surface to prevent vibration and ensure proper alignment. Fourthly, adequate ventilation should be provided to prevent overheating. Fifthly, the drive parameters should be configured correctly to match the motor characteristics and the application requirements. Regular maintenance is essential to ensure the reliable operation and long lifespan of alternating current motors and drives. Firstly, the motor and drive should be inspected regularly for signs of damage or wear. Secondly, the motor bearings should be lubricated as recommended by the manufacturer. Thirdly, the motor and drive should be kept clean and free of dirt and debris. Fourthly, the motor and drive operating parameters such as voltage, current, and temperature should be monitored regularly, and any abnormalities should be addressed promptly. Fifthly, the cooling fans should be checked to ensure they are operating properly and keeping the motor and drive cool. Troubleshooting common problems with alternating current motors and drives requires a systematic approach. Firstly, if the motor does not start, check the power supply, wiring, and motor overload protection. Secondly, if the motor is running but overheating, check the ventilation, load, and motor windings for insulation breakdown. Thirdly, if the motor is vibrating excessively, check the alignment, balance, and motor bearings. Fourthly, if the drive is displaying error codes, consult the manufacturer's manual for troubleshooting steps. Fifthly, use a multimeter to check the voltage and current levels in the motor and drive circuits to identify any faults. Several advanced features are available in modern alternating current motors and drives that can further improve efficiency and performance. Firstly, energy-efficient motors with optimized designs can reduce energy consumption and operating costs. Secondly, advanced drive control algorithms such as sensorless vector control can provide precise speed and torque control without the need for motor feedback sensors. Thirdly, built-in programmable logic controllers, or PLCs, can allow the drive to perform complex control functions without the need for an external controller. Fourthly, remote monitoring and control capabilities can allow users to monitor and control the motor and drive from a remote location. Fifthly, predictive maintenance features can use data analytics to predict potential failures and schedule maintenance proactively, minimizing downtime and maximizing equipment lifespan. The selection, installation, maintenance, and troubleshooting of alternating current motors and drives are critical aspects of ensuring the reliable and efficient operation of industrial equipment. By carefully considering the application requirements and following best practices, users can maximize the performance and lifespan of their alternating current motor and drive systems. Motors are classified by definite purpose, general purpose, and special purpose. Definite purpose motors are designed for specific applications like HVAC equipment, where the motor's characteristics are tailored to the load. General purpose motors are designed for a wide variety of applications and are available in standard sizes and ratings. Special purpose motors are designed for unique applications requiring specific performance characteristics. When selecting a motor, consider the horsepower required to drive the load. Oversizing the motor can lead to inefficiencies, while undersizing can result in overheating and premature failure. Match the motor's speed to the application's needs. Synchronous speed is determined by the number of poles in the motor and the frequency of the power supply. Slit speed is the difference between the synchronous speed and the actual rotor speed in induction motors. Choose the appropriate motor enclosure based on the environmental conditions. Totally enclosed fan-cooled, or TEF, motors are suitable for dirty or dusty environments, while open drip-proof, or OP, motors are suitable for clean, dry environments. Select a motor with the appropriate voltage and frequency ratings for the available power supply. Ensure the motor's insulation class is suitable for the operating temperature. Higher insulation classes allow for higher operating temperatures. Consider energy efficiency when selecting a motor. NEMA premium efficiency motors offer significant energy savings compared to standard efficiency motors. When installing a motor, ensure proper alignment between the motor and the driven equipment to minimize vibration and wear. Use flexible couplings to accommodate minor misalignments. Provide adequate ventilation to prevent overheating. Ensure the motor is properly grounded to prevent electrical shock hazards. Follow the manufacturer's wiring diagrams and instructions for proper connections. Periodically inspect motors for signs of wear or damage. Check the motor bearings for proper lubrication. Clean the motor to remove dirt and debris that can impede cooling. Monitor the motor's operating temperature to detect potential problems. Check the motor's voltage and current to ensure they are within acceptable limits. When troubleshooting motor problems, start by checking the power supply. Verify that the voltage and frequency are correct. Check the motor windings for continuity and insulation resistance. Use a megometer to test the insulation resistance. Look for signs of overheating, such as discolored windings or a burnt smell. Check the motor bearings for excessive noise or vibration. Replace worn or damaged bearings promptly. Consider using a motor management system to monitor motor performance and detect potential problems early. Variable frequency drives, or VFDs, are used to control the speed of alternating current motors. They do this by varying the frequency of the power supplied to the motor. VFD can improve energy efficiency, reduce mechanical stress on equipment, and provide precise speed control. VFD consists of several main components, including a rectifier, a direct current bus, and an inverter. The rectifier converts the incoming alternating current power to direct current power. The direct current bus smooths and filters the direct current power. The inverter converts the direct current power back to alternating current power at the desired frequency and voltage. VFD can be controlled using a variety of methods, including local keypads, remote control signals, and network communications. When selecting a VFD, consider the motor's voltage, current, and horsepower ratings. Choose a VFD with sufficient capacity to handle the motor's full load current. Select a VFD with the appropriate enclosure rating for the environmental conditions. Ensure the VFD is compatible with the motor's control scheme, such as volts per Hertz or vector control. Consider the communication options available, such as Ethernet, Modbus, or Profibus. When installing a VFD, follow the manufacturer's instructions carefully. Ensure proper grounding and wiring practices. Provide adequate ventilation to prevent overheating. Configure the VFD parameters to match the motor's characteristics and the application requirements. Regularly inspect the VFD for signs of wear or damage. Check the cooling fans to ensure they are operating properly. Monitor the VFD operating parameters, such as voltage, current, and temperature. When troubleshooting VFD problems, start by checking the input power supply. Verify that the voltage and frequency are correct. Check the VFD display for error codes. Consult the manufacturer's manual for troubleshooting information. Use a multimeter to check the voltage and current levels in the VFD circuits. Ensure that the motor and VFD are properly matched to prevent damage. Consider using harmonic filters to reduce harmonic distortion caused by the VFD. Harmonic distortion can cause problems with other electrical equipment. VFD can be used in a wide variety of applications, including pumps, fans, conveyors, and compressors. They are particularly useful in applications where variable speed control is required to optimize performance and energy efficiency. Understanding the principles of alternating current motors and drives is essential for anyone working with electrical equipment in industrial settings. By following best practices for selection, installation, maintenance, and troubleshooting, you can ensure the reliable and efficient operation of your motor and drive systems. The torque speed curve of a motor shows the relationship between the motor's torque output and its speed. The starting torque is the torque produced by the motor when it is first energized. The pull-up torque is the minimum torque produced by the motor during acceleration. The breakdown torque is the maximum torque the motor can produce without stalling. The full load torque is the torque produced by the motor at its rated horsepower and speed. Understanding the torque speed curve is essential for selecting the right motor for a given application. Different types of loads require different torque speed characteristics. Constant torque loads, such as conveyors, require a constant torque output over a wide range of speeds. Variable torque loads, such as centrifugal pumps, require a torque output that increases with speed. Constant horsepower loads, such as machine tools, require a constant horsepower output over a wide range of speeds. Motor protection devices are used to protect motors from damage caused by overloads, short circuits, and other faults. Overload relays protect motors from damage caused by excessive current draw. Fuses and circuit breakers protect motors from damage caused by short circuits. Ground fault relays protect motors from damage caused by ground faults. Surge suppressors protect motors from damage caused by voltage surges. Phase monitors protect motors from damage caused by phase imbalances. Proper motor protection is essential to prevent costly downtime and repairs. The National Electrical Code, or NEC, provides guidelines for the safe installation and operation of electrical equipment, including motors and drives. NEC Article 430 covers motors, motor circuits, and controllers. NEC Article 430.52 specifies the requirements for motor overload protection. NEC Table 430.148 provides full load current values for alternating current single-phase motors. NEC Table 430.150 provides full load current values for alternating current three-phase motors. Adhering to the NEC is essential for ensuring the safety of electrical installations. Power quality refers to the characteristics of the electrical power supply. Poor power quality can cause problems with electrical equipment, including motors and drives. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Voltage sags are temporary decreases in voltage. Voltage swells are temporary increases in voltage. Harmonics are distortions of the sinusoidal waveform of the electrical power supply. Transients are short-duration, high-voltage spikes. Power quality problems can be mitigated using various techniques including surge suppression, harmonic filtering, and voltage regulation. Regularly monitor power quality to detect and address potential problems. Motors with encoder feedback can provide precise speed and position control. Encoders provide feedback signals to the motor controller indicating the motor's speed and position. This feedback can be used to improve the performance of applications requiring precise control. Encoders are commonly used in servo motor systems and other high-performance applications. Predictive maintenance is a maintenance strategy that uses data analysis to predict potential equipment failures before they occur. By monitoring motor performance data, such as temperature, vibration, and current, potential problems can be identified early. This allows maintenance to be scheduled proactively, minimizing downtime and repair costs. Predictive maintenance can improve the reliability and efficiency of motor systems.